setters, welcome to today's Grade 12 Physical Sciences show. Today we have a special revision lesson on physics. We have selected highlights from lessons shown earlier in the term to help you revise this term's work. So please post your comments and your questions on our Facebook page or on Twitter @LearnExtra so we can help you with your revision. You can also download the show notes for today's lesson from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
So this was from the prelim paper in 2008. It says, consider the electric circuit below and answer the questions that follow. Assuming no internal resistance, assuming we can ignore the resistance of everything else, we're just going to go from here. Now, first thing you should do, now whether you know that conventional current always goes from positive to negative, or you do it the other way around, makes absolutely no difference, okay? What you really should do is have a couple of highlighters or more pens, it's up to you. What I am going to do is we've got to make sure you can actually see this. So I'm going to try another pen, see what happens, okay? Is you take your highlighter and you start from the cells, because that's where it originates, okay? And you can't even see that. So, no, you can't see that either. Can you see this one? No. Alright, so we're not going to do that. Let's use highlighters. Okay, so as you can see, part of my circuit's now turning yellow. It was white. This is series. It goes through this resistor. And now I've got to this point. Over here, we now have a choice. Okay, so now I change my highlighter. I change pens because now we're going to go to green to the top. And I'm using a different color at the bottom, because they're different values. If the two resistors in parallel were the same value, so say they were both 5 or they were both 15, I would use the same color pen, okay? But they're different values, so I know it's going to separate. And then I remember that, well, when they come back together, I've still got to have the total. It can't have disappeared, okay? Current can't have disappeared. So whatever current goes through here, it's the same current that's going through here, okay? And in fact, now the very first question they ask is for you to calculate the magnitude of that current. First thing you need to do when you look at a question like this is look and see what the easiest equation to use is, okay? I know what V total is, because that's the 60 volts. It has to be, okay? It can't be anything different. So we go, okay, I know that my total voltage is 60 volts. They want the magnitude of the current. So what they're asking you for here, grade 12s, is they're saying to you, what is the total current? Okay, they want here, I total. Okay, so now we say to ourselves, well, to get I total, if this is the easiest equation, that's the most basic. So we go, okay, R equals V over I. I know I'm going to probably have to use V total because I've got it. I want I total, which means I'm probably going to need R total. Okay? I'm going to need total resistance. So now we go, okay, can't just add them all together. Why? Because I have a parallel section. So what I actually need to do is I need to work out what my R parallel is, okay? So this is what we're going to do. I really need you to try this on your own. Thinking about what I told you about how to work out R parallel earlier with the equation, okay, because I want to see if you can do it. I'm going to leave it up to you. We're going to take a short break. While we're doing that, you need to work out R parallel for me. In fact, total resistance, see if you can get an answer, and then we'll come back to it and I'll answer it in the next section. I say to you, please try and work out your total resistance. So the first thing we're going to do is we need to work out the resistance in parallel, okay? So it was 15 and 5, okay? So what that means is we're going to go over here and we're going to try and do this so you can actually read it, because we know I have issues, is we're looking for our resistance in parallel. Guys, this is your equation. You must write it down. Okay? That means you're now going to go 1 over 15 plus 1 over 5. Now, I'm about to show my age, grade 12s, because I know that you can press special buttons on your calculator and it'll do the fraction for you. I don't know how to do that, okay? So
Just tell us. How old are you?
No, I'm not telling you. Maybe we'll do a prize from guessing. I'll give the... yeah, anyway, no, that's not a competition. Grade 12s, do not go and guess my age on that book.
Yeah, I've got a few answers from my side about how old you are.
21.
Of course you are.
Plus that. Moving on. Okay, let's do science. Point is, okay, I know that on your calculators, okay, and if you look at the calculator, you've got the fraction button somewhere, and I know you can do it as really, if you can do it on your calculator, go ahead. I'm not going to because I need to show you something, okay? When we do this old school, the common denominator is 15, okay, so this is 1. We're going to add 3, and what happens is we get that 1 over RP equals 4 over 15. Now, do it on your calculator, you're going to get 4 over 15. We're happy you don't have to show this middle step. From here, hopefully some of you realize, well, actually that's 1 over resistance in parallel. I need the total resistance, okay? I need the resistance in parallel. This doesn't help me, so we need to invert this answer. But now what you guys do is you do this. You go, now I've got to invert it, so it's 15 over 4. And then I'll stop marking. Because what you've now written is you've told me that 4 over 15 is equal to 15 over 4. No, it's not. RP is equal to 15 over 4. Another thing, and I know this is a maths issue, and there's nothing wrong with what you've been taught in maths, but it becomes a problem here in science. Never leave your answer as a fraction, okay? Never, never, never. You need to, and in fact, if you go 15 divided by 4, okay, ooh, maybe we should do it properly, 15 divided by 4. See, that's not what I want. I want 3,75, okay? A lot of your questions are worked out with the decimal, so they actually work out quite nicely for you. All right, so either you add it to something else, gives you a nicer number, gives you a nice value for current, you don't get lots of funny decimals, so sometimes they are worked out like that, okay? So please do not leave it as a fraction. Also, I now need to take this, because what we've done is we've gone, well, my R parallel, this is actually 3,75. I need to add this to the 20, okay? I need to add it to the 20 because they're actually in series with each other, okay? Once we've got 15 over 4, which now we need to add to 20, we're just making our life difficult, okay? Don't do it, because now we're going to add it to the 20, okay? So my total is R parallel plus the R that we have at the top there. So it's 3,75 plus 20, which gives me 23,75. Okay, which I know just looks like the most ridiculous answer in the question in the world still, but it doesn't matter. We're still on the right track. Still not done though, because the question was calculate total current. So what I'm going to do is I'm going to do it a little bit further down, because once again, I did not leave myself enough space. Okay, so R total equals V total divided by I total. Now, we said that my resistance was 23,75. My total voltage is 60. And to get I total on its own, we're going to now we're going to take it over to the other side. So we're going to get I total is 60 divided by 23,75. Okay, so watch, we're going to go 60, not 600. See, this thing doesn't like me. 60 divided by 23.75. There we go, and we don't want it as a fraction, and we get 2,53. Okay, remember it's got to be rounded off. So we get
so many people got that right, actually.
Oh, it's because they're all brilliant.
Such geniuses.
And you know what? That makes me very happy. It really does, and I'm really not being facetious or sarcastic about that, guys, because if there's one section in your exam that, and I know it's just me because I love the section that I really think is an easy section, it's circuits, and that's practice, practice, practice. So well Done. Okay, so we get 2,53, so that's the current. And I'm going to go back to my circuit diagram, and I'm actually going to write it in. Okay? Because you never know, I might need it a little bit later on, and we don't want to have to keep reading the question. Now they say to me, calculate the potential difference across the 15 ohm resistor. The 15 ohm resistor is in parallel. Because it is in parallel, what we need to recognize here is whatever voltage, let me do this in another color actually so we can see it, because whatever voltage is over that 15 ohm resistor is the same as the voltage over the parallel. Okay? So in other words, the voltage over the 15 ohm resistor is equal to the voltage over the potential difference over the parallel section. Okay? Notice what I've done here, grade 12s, is I've labeled this 15 ohms and parallel. Okay? Because if I just go V equals to V, what are we referring to? What are we trying to get to? And if we don't write down where we're trying to get, it becomes very, very difficult. Okay? To get the voltage in parallel, we go, well, I know R parallel. We worked it out. We just did it. It's 3,75. And the total current between those two branches is 2,53 is what we just did. I can do this, so watch what happens. So V parallel, okay, is going, let's not go that way, sorry, I lied. R parallel is V parallel over I total. Now, if you want to go V equals I times R, you're welcome to. Okay, the only reason why I don't do it is because the equation given to us is R equals V over I, and often it's easy to make a mistake with putting V as the subject. Okay, so this is more a, let's just hedge our bets here. Let's make sure we get the marks for the things we can get. R parallel was 2,53. V parallel is what I'm looking for. My current was 2, jeez, Uni, did you not notice I made a mistake?
I'm actually not looking on.
That's what she's not even listening. She's fallen asleep. Okay, that's actually 3,75. That's 2,53. Now we've got it the right way around. Okay.
Oh, yes.
Thank you.
Because the thing is, I'm looking at the answers. That's why I wasn't looking at you. So I was wondering what you're writing down. So I was looking.
Whatever.
I'm with you.
And then when we multiply them together, we get 9,49 volts.
You must find your mistakes, you know? Okay, guys, I hope you're enjoying this revision session. If you are struggling and need help, please post on the page or send your questions to the Learn Extra Help Desk. The links are on our Facebook page. But now it's time to take a very quick break. Don't go away. We'll be right back. Welcome back, Mindsetters. Even though we are selecting highlights from previous shows, you can still follow me on Twitter @LearnExtra, or you can post or comment on our Facebook page. Now, let's do some more revision.
So it tells us that the following experiment was performed by a group of learners, science students, and they were doing we were asked to read this little introduction about internal resistance of a cell or a battery, and it says when we measure the voltage of a battery, we say we're measuring the terminal potential difference of the battery. So across the battery, we see the battery or the cell was labeled 1,5 volts. In the diagram on the right is not supplying any current. So take a look over here, no current, okay? And we're told that it is 1,5 volts. That's the reading on the voltmeter. Assuming that the voltmeter has an infinite resistance. Voltmeters usually have a very large resistance, so we say the potential difference measured under these conditions is called the EMF, E, and EMF is 1,5. So guys, that's the first step. The current is not flowing. There is no work being done in the external circuit. Maximum potential that this cell can deliver is 1,5 volts. Now, look what happens. Different circuit. It's a closed circuit now. The battery is now connected to a resistor and is supplying a current of 0.2 amps. The terminal potential difference is now 1.3 volts. So over here, 1.3 volts. It's doing some work in the external circuit. That's what this battery is now measuring. Take a look here. If we say it has high energy over here, through the ammeter, doesn't use up energy. Over here, it has got to the battery, or to the resistor at least, and now on this side, it's at a lower potential. So between there and there, between the orange and the pink, is what the voltmeter is reading. Different types of energy. The current, because it was in series, is the same, but the energy is different. It's like what happens when you go shopping. Your bank balance, when you go into the shop, is at a certain level. When you come out from the shop, there's a difference in potential. There's a difference in the amount of money that you can buy, in your spending potential. Same things happened here. There's a drop in potential. And that's what's being measured here. This is the load, the V load, that is being measured here. Now, the same battery is now supplying a current of 0.4 amps. The potential difference across the terminal is 1.1 volts. 1.1 volts. Hey guys, it's now a difference. It started off still the same. Let's just keep our colors the same. Started off with orange. Still the same. But when it came here, it changed. It split. The current divided, but the potential was still the same across here and here. But now on the other side, it wasn't down to the pink anymore. It's gone down to the green level. So hopefully you can see, if you mark your potential regions of the same potential on a diagram, you'll be able to see where there's been a change in potential, where there's been a drop. And over here, we connected things in parallel. So just take a note of this diagram, and you can see that the voltmeter is reading the difference between orange and green on this side. Across, if I connected a voltmeter here, it would still read between orange and green. And this one would still read between orange and green. So they would all be the same reading, because orange to green is 1.1 volts. Across any places between orange and green, those regions of potential would be the same. Okay, so please be aware of that. But that's kind of crazy. Originally, we had 1.5, and we've dropped all the way down to 1.1. What's happened? Let's look at the questions. That's exactly what the questions are asking. So it tells us that when a cell is not supplying a current, what is the value of the terminal potential of the battery? What is this value known as? So in this case, what was the reading? We said E was 1.5 volts. And it's known as EMF. Okay? EMF stands for electromotive force. You need to know that. It's like the pushing power of the battery. It's the amount of energy that it can push those charges through the closed circuit with. Okay. Now, what's the next thing? What happens to the terminal potential as the current in the circuit increases? Have a look. What happened over here? Over there was 0 amps. Over here, the current was measured at 0.2 amps. Notice that was 1.3 volts. Then this one, 0.4 amps. So what's happened to the current? The current doubled, went from 0.2 to 0.4. And what's happened to the potential difference? Read it out of the diagram, if you can see, from 1.3 to 1.1. So what's happened? It's decreased. What's happened? The terminal potential, V, decreased. Sure. I hope you've got that. Make sure you understand that in this scenario, as the current has increased, the potential difference decreased. The terminal potential difference. Remember from our summary, we're dealing with the V load part. That's what we're dealing with. So they then ask us, the next part of the question is, what is lost voltage? Well, we started with EMF being 1,5 volts, and we had V load in this final circuit as being 1,1 volts. There's a difference between these. There's the V internal, and that was the difference between those of 0,4 volts. These two add together will always give you the same EMF. So lost volts, or lost voltage, hasn't actually been lost. It's using up energy to push through the cells, to push through the battery. We need to recognize that's where it's happening. And so that's the next question. Explain why the cell, I don't understand where this is going, but explain why the cell loses voltage. It's because there's energy used up inside the cell. Okay, what you need to recognize, inside that cell, there's a chemical reaction. And we've now got to move charges from the negative terminal to the positive terminal. Positive charges from the negative terminal to the positive charge. And that requires some work. It doesn't flow normally. Normally, from the positive terminal, the charges are attracted to the negative terminal. Now they get back to the negative terminal. They've got to be pushed. And as the cells get older as well, there's additional chemical waste, products that are produced, that makes it more difficult for these charges to get through. Now, I know that in reality, that it's not actually the positive charges moving, but I like to think of it as positive charges, because conventional current is the movement of positive charge around the circuit. In fact, what we know it is, at the same time as the positive charges are moving, or we say they're moving because they don't actually physically move, it's the electrons, the negative charges, that move from the negative terminal all the way around to the positive terminal, but the electrons still need to get from the positive terminal back to the negative terminal. And so that's why we've called it, there's this two-way flow. Positives move one circuit, negatives move the other, and we've got to decide which way is current. We've decided we're going to take the route of defining it as positive. It's really only in metals and in circuits that we use here that we have non-moving positive charges. But the idea is that we will have. In electronics and in plasmas and all over the place, we do get other positive charges moving. Even in solutions, you get positive charges moving. So we'll stick to the convention. Right, last question is now the calculation bit. And let's hope we can get some space here. And the board can extend our page a little, and we can start to interact with the question. But it's giving me a little bit of uphill, so I can't really read. So it says, using a formula, calculate the lost volts. So I don't really like the word lost volts. I'm going to say it's V internal. Okay? Calculate the internal resistance of the cell in the experiment above. So there are two things that we need to know. First of all, the equation is E is equal to V load plus V internal. And then we can break that apart and say V internal is I times R, where the capital R is the external resistance, and the I is still the same because it's in series, times the little r. Okay, and what we've got to do is we have to find the IR part, and we've got to find the R part. So there are two parts to this particular question. Let's see what we know. I'm going to say that we know that E is 1,5. So there's no doubt about that. Then we've got to make some choices. We were given current and V load for both those two circuits. And I'm going to just choose the easier one. I'm going to choose the number. If you take a look here, I'm going to choose this one over here where the current was 0,2 amps and the V load was 1,3, because there's a single resistor, and it makes it just a little bit easy in terms of that. We don't know what that resistance is, but I don't think we really need it. So let's just check that out. So remember, the load was 1,3 volts. So what I can do is I can say I know that V load was 1,3 volts. And I'll put the V there. I know that the current was 0,2 amps. And I'm putting it in brackets so that we don't make a mistake. I know that's R, and I know that this was 1,5 volts. Now, guys, you don't need to put the units in. I was just stressing the units to make sure that we don't make mistakes with them. Because you don't suddenly want to put current in and recognize that current is in amps and it's not in volts. Amps times ohms gives us volts, so we are happy with that. So I'm just going to carry on and use the calculator now to work out the little r. And let's move it down and extend the page. And the first thing I'm going to do is I'm going to say 1,5 minus 1,3 equals 0,2 times little r. And if I do that calculation, I recognize that's 0,2, which is quite nice, and that's 0,2 over here, little r. What am I going to do? Divide both sides by 0,2, and I get little r is equal to 1 ohm. Okay, guys, I could check it and make sure that it's the same answer with the other circuit. I'm going to leave that for you to do. Okay, let's move on. We've calculated, let's give the answer. We wanted V internal, which was equal to V lost, is now going to need to be calculated. We haven't quite finished, so that's going to be I times little r, which is 0,2 times, in brackets, 1. So the V internal is 0,2 volts. That's what was lost. Please make sure you answer the whole question. Don't just get to the answer of R is equal to. Make sure you've answered it. Check back to the question, and you'll see that they asked us for both those things. They asked us for the internal resistance of the cell and the lost volts. Calculate the lost volts and the internal resistance, and we've done both of those.
I think it's time for a break now, so don't go away. We'll be right back. Welcome back from the break, guys. Doing revision is really important, so I hope you are enjoying this lesson. I'd love to chat to you on our Facebook page or on Twitter, so please let us know how you are doing. Enough of the chat, now it's time to get back to some more revision.
Here we go to a prelim paper that was written in 2008, and it tells us that we've got a waveform. On the page is a graphical representation of the variation of voltage versus time for an alternating current. And it's exactly what we've looked at before. Just to remind you that we've got the zero value over there. This value here is V maximum. And in that formula that we just derived, or I showed you how to derive it, where we're looking for VRMS, which is like the average, we would have taken the V maximum, squared it, divided it by 2, and then take the square root. And that's why we get VRMS is equal to Vmax divided by the root of 2. Now, what they're asking us to do is, first of all, to explain the advantage of using alternating current at power stations. I've given you these advantages. First of all, it's easy to generate, easier to generate AC. But that's not the real reason that they're looking for. The real reason is that it's cost effective to take from the power station to transmit, or to carry to transmit. In other words, you don't want to have a great big generator running in your back garden that you can hardly hear yourself speaking over dinner, because that's just not going to be comfortable. So we want to build our houses and our cities away from where the power stations are. And to do that, we need to have an easy way to transmit it. And the reason alternating current is so useful is that it can be transformed. It can be transformed to have low current and high voltage. Now, let me just explain. There are two aspects to that. To transform something, you need a changing magnetic field that will allow you to produce a changing changing current or changing induced EMF. The alternating current provides in the coil that it runs around a changing magnetic field. So on the secondary coil, it is allowed to induce a changing potential difference again. So we can step it up or step it down. The reason we want to make it low current is that from our power calculations, we should remember that power is equal to I squared times R. Now, if we have high current, or even any current, the power, that current has to be squared to calculate the energy lost. So if we think about it, we just need to make sure we reduce the current, keep the resistance constant, and we can reduce the energy lost. So that's the really important part. I hope that explains it fully. The next part that we're asked to do is to calculate the average power. So guys, now I need you to understand, wherever you see average power, we must say average power is equal to VRMS times IRMS. And the trickiest thing that you've got to do in this section is to recognize what values you must work with. Whenever you're working with power and with any of the other formula, please specify as a subscript what you're dealing with. We're asked to find average power, and it tells us if the RMS current produced is 13 amps. So what we need to go back to is some further information over here, and you will see that what we're given on the graph, read the whole question, we're given that Vmax over here is equal to 325 volts. So if I know that Vmax is 325, I've been given the IRMS, so I know IRMS is 13 amps. I now need to find VRMS. So I'm going to use that equation just now, but I'm going to work over here to find VRMS. And I know that VRMS is Vmax divided by the square root of 2. Substitute my values, and if I remember correctly, it was 325 volts. So 325 divided by root 2 will give me VRMS. So let's put that on the calculator, and we're going to say 325 divided by the square root of 2, and we're going to get the answer as 229.8. 229.81. 229.81. Now, you might say, well, why did I round off there? Why didn't I keep my values on the calculator? It's really important. They're really strict. They want you to round off at every stage to 2 decimal places, just so that we can be consistent. So there's the potential difference. We're now going to take those values and put them into the power calculation and say 229,81 put it in brackets. So we're not thinking about x's or y's or anything else. You don't need to put the units in. I'd strongly advise you not to put the units in. And we then make sure that we start again. And we say 229,81 times 13. And that will give us 2987,53. 2987,53. 2987,53. And give the right unit. It's power, so it's watts. Okay, guys? Hope you see that it's not that difficult. As long as you isolate, we've got these 2 factors. The RMS, which is like your average, and you've got your maximum.
So question 1 is they give you the work function of 3 metals, and it's shown in the table below. So we have aluminium, which is 6,54 times 10 to the minus 19, zinc 6,89 times 10 to the minus 19, silver 7,56 times 10 to the minus 19, all in joules. What you need to realize here, grade 12s, is that the work functions are all very small. Okay, these values are all very tiny. Electrons are tiny little things that doesn't require a lot of energy to get them moving as such. Now they ask you, give a reason why different metals have different work functions. Well, different metals have different electronic structures, so they have different ionization energies, which means that that a different amount of energy is required to release the electrons. Okay? So because their structures are different, they have a different number of electrons, they have different numbers of orbitals, and that's energy levels, they require different amounts of energy, okay? That was easy. Now it says, light of wavelength 2,3 times 10 to the minus 7, so that's my first piece of information. So that's wavelength, let's just write it down, is shone onto metal X, we don't know what metal X. The average speed, this is going to be a mean one, of the emitted electrons is 4,78 times 10 to the 5. So V is 4,78 times 10 to the 5. And now they say to you, identify metal X by performing a relevant calculation. So what they are implying is that metal X is one of these 3 metals. So the question is actually saying to you, find the work function. Find WO. So we look back here and we go, well, that wavelength is not going to give me my threshold frequency, simply because the electrons came off with a velocity. So if the electrons come off with a velocity, it means that the light I used is above threshold frequency. That's the first thing. That automatically tells me that I'm going to need to use this equation, where we said E equals WO plus EK. Okay? So now we go and we say, okay, well, WO is what I'm looking for. So E would be HF. I'm not going to change W to HFO because I want WO as it stands, okay? So I'm going to leave it as WO. I do have to do something with the EK though, because I only have velocity here. So this becomes a half mv squared. So now we think about this, and this is exactly how you go through this in your head, grade 12s, is you say, okay, H is fine. That's Planck's constant. F, hang on, wait, I wasn't given F, but I do know that C equals F lambda. So F is actually C over lambda. So over here, I can now change this to HC over lambda. Okay? I want WO, so that's what I want. So I'm going to leave that there. Ooh, now we go here and we say, I know V, and I bet you anything you're now going, hang on, wait, Tracy. What mass do we use? Guys, this is not something you're expected to know. In fact, I can't even tell you what the mass of an electron is without looking it up. On your information sheet, it will say, on your data, okay, your constants, it will give you the mass of an electron. So that means I actually know that value too. I have more than enough information. Now, that's the equation I'm going to use. So when you write this down, let's not actually write that there, because that was for us. But this is the equation I'm going to use to work it out. So let's put in everything we know. Okay, so H is 6,63 times 10 to the minus 34. C, speed of light, hopefully you all know this, 3 times 10 to the 8, I almost said 6, that would have been sad. Lambda, if we go back to the question, they said it was 2,3 times 10 to the minus 7. I want WO. Okay, so this becomes a half. The mass of an electron, you will actually go and look that up because I don't know it off by heart. But when we look it up, we get that it's 9,11 times 10 to the minus 31. It is the most ridiculously tiny little thing, but that's okay. And the speed, which was given to you in the question, is 4,78 times 10 to the 5 squared. And you know what, grade 12s? You've done the science. What's left after this is a maths issue. Now it's about how you use your calculator. And in this one, you know what? Do it in parts. You can't do this all at once. It's going to get very messy. So let's do this on this side, and I'll move it back in a second. So let's do the first one. So we're going to go 6.633 to the minus 34 times 3 to the 8. All of that's going to be divided by 2.3 to the minus 7. And we get 8,64. We're going to round it off straight away. So 8,65 times 10 to the minus 19, okay? 8,65. Let me just do this a little bit lower down. So 8,65 times 10 to the minus 19. All right. Now let's do the other side. So I'm going to put it on this side so you can see where I'm getting my values from. Okay, hang on. Let's just do this quickly so you can see. Okay, so now I'm going to do the half. All right. So we're going to go 0.5, that's a half, times 9.11 exponent minus 31. All right. Times, okay, now the next one has to be squared. Please don't forget out the square. It's so easy to do that. So I'm going to put it in brackets, 4.78 to the 5, and that all needs to be squared. Ooh. Someone's doing all sorts of weird and wonderful things in the studio, but it's all right. We'll ignore it.
Fine, we'll ignore
That gives me 1,04, and if you look at it, it's 1,0407, so rounding off 1,04 times 10 to the minus 19. Now, I know I'm sort of in the right area because this was 8,65. That was times 10 to the minus 19, 1,04 times 10 to the minus 19. So to get WO, I'm going to end up going 8,65 times 10 to the minus 19 minus 1,04 times 10 to the minus 19. Okay, we'll pretend that the 19 came out over there. So let's put that in. So we're going to go 8.65 to the minus 19 minus 1.04 to the minus 19. And we get 7,61 times 10 to the minus 19. Okay, so we've got 7,61 times 10 to the minus 19, and that's in joules. But are we done yet? Hopefully somebody is screaming, no, Tracy. Yes, I don't know where that came from. And the answer is no, we're not, because the question was to identify metal X. So we've got 7,61 times 10 to the minus 19. So we go here and we go 7,61. The closest one to that is silver. It's not exactly that. The reason why you don't get quite exact that number is, that was terrible. Why you don't quite get that number is because of rounding. All right, because of the rounding off, there's issues. So that's as close as we're going to get. That's 7,56 times 10 to the minus 19. Okay, now I actually left out a question on this because the next question from this exam was, what does this experiment show about the nature of light, or what property of light does it show? And the answer to this one always is it shows that light has a particle nature. Okay, you can't say it shows that light is a particle because we can't say that definitively. What we can say is that light behaves like a particle. Light behaves like a wave, so it has a wave nature and it has a particle nature. Okay?
Thanks for joining me and for chatting to me during the show. Please visit our website learn.mindset.co.za to get the notes and to watch the videos from earlier in the year. And remember, we are here to get you through the year, so stay connected. Goodbye.
Is, because that's the 60 volts. It has to be, okay? It can't be anything different. So we go, okay, I know that my total voltage is 60 volts. They want the magnitude of the current. So what they're asking you for here, grade 12s, is they're saying to you, what is the total current? Okay, they want here, I total. Okay? So now we say to ourselves, well, to get I total, if this is the easiest equation, that's the most basic. So we go, okay, R equals V over I. I know I'm going to probably have to use V total because I've got it. I want I total, which means I'm probably going to need R total. Okay? I'm going to need total resistance. So now we go, okay, can't just add them all together. Why? Because I have a parallel section. So what I actually need to do is I need to work out what my R parallel is, okay? So this is what we're going to do. I really need you to try this on your own. Thinking about what I told you about how to work out R parallel earlier with the equation. Okay, because I want to see if you can do it. I'm going to leave it up to you. We're going to take a short break while we're doing that. Calculator, go ahead. I'm not going to because I need to show you something, okay? When we do this old school, the common denominator is 15. Okay, so this is 1. We're going to add 3. And what happens is we get that 1 over RP equals 4 over 15. Now, do it on your calculator. You're going to get 4 over 15. We're happy you don't have to show this middle step. From here, hopefully some of you realize, well, actually that's 1 over resistance in parallel. I need the total resistance. Okay, I need the resistance in parallel. That doesn't help me. So we need to invert this answer. But now what you guys do is you do this. You go, I know I've got to invert it, so it's 15 over 4. And then I'll stop marking. Because what you've now written is you've told me that 4 over 15 is equal to 15 over 4. No, it's not. RP is equal to 15 over 4. Another thing, and I know this is a maths issue, and there's nothing wrong with what you've been taught in maths, but it becomes a problem here in science. Never leave your answer as a fraction. Okay? Never, never, never. You need to, and in fact, if you go 15 divided by 4, okay, ooh, maybe we should do it properly. 15 divided by 4. See, that's not what I want. I want 3,75, okay? a lot of your questions are where it originates, okay? And you can't even see that. So, no, you can't see that either. Can you see this one? No. All right, so we're not going to do that. Let's use highlighters. Okay, so as you can see, part of my circuit's now turning yellow. It was white. This is series. It goes through this resistor. And now I've got to this point. Over here, we now have a choice, okay? So now I change my highlighter. I change pens because now we're going to go to green to the top. And I'm using a different color at the bottom because they're different values. If the two resistors in parallel were the same value, so say they were both 5 or they were both 15, I would use the same color pen, okay? But they're different values, so I know it's going to separate. And then I remember that, well, when they come back together, I've still got to have the total. It can't have disappeared, okay? Current can't have disappeared. So whatever current goes through here, it's the same current that's going through here, okay? And in fact, now the very first question they ask is for you to calculate the magnitude of that current. First thing you need to do when you look at a question like this is look and see what the easiest equation to use is, okay? I know what V total
Hello Mindsetters, welcome to today's Grade 12 Physical Sciences show. Today we have a special revision lesson on physics. We have selected highlights from lessons shown earlier in the term to help you revise this term's work. So please post your comments and your questions on our Facebook page or on Twitter @LearnExtra so we can help you with your revision. You can also download the show notes for today's lesson from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
So this was from the prelim paper in 2008. It says, consider the electric circuit below and answer the questions that follow. Assuming no internal resistance, assuming we can ignore the resistance of everything else, we're just going to go from here. Now, first thing you should do, now whether you know that conventional current always goes from positive to negative, or you do it the other way around, it makes absolutely no difference, okay? What you really should do is have a couple of highlighters or more pens. It's up to you. What I am going to do though is we've got to make sure you can actually see this. So I'm going to try another pen, see what happens, okay? Is you take your highlighter and you start from the cells, because that's where you need to work out R parallel for me. In fact, total resistance, see if you can get an answer. And then we'll come back to it and I'll answer it in the next section. I said to you, please try and work out your total resistance. So the first thing we're going to do is we need to work out the resistance in parallel, okay? So it was 15 and 5, okay? So what that means is we're going to go over here and we're going to try and do this so you can actually read it because we know I have issues, is we're looking for our resistance in parallel. Guys, this is your equation. You must write it down, okay? That means you're now going to go 1 over 15 plus 1 over 5. Now, I'm about to show my age, grade 12s, because I know that you can press special buttons on your calculator and it'll do the fraction for you. I don't know how to do that, okay? So
Just tell us, how old are you?
No, I'm not telling you. Maybe we'll do a prize from guessing and I'll give the... yeah, anyway, no, that's not a competition. Grade 12s, do not go and guess my age on that book.
Yeah, I've got a few answers from my side about how old you are.
21.
Of course you are.
Plus that. Moving on. Okay, let's do science. Point is, okay, I know that on your calculators, okay, and if you look at the calculator, you've got the fraction button somewhere, and I know you can do it as really, if you can do it on your